In this section, we're going to introduce these things called impulse functions, see an example of one, and then talk about a special kind of impulse function that's called the Dirac delta function. We're going to find its Laplace transform and see what that does to applications such as the spring mass problem. So impulse functions are functions that represent a large magnitude over a short period of time. In a sense, it's on for a very short period of time and off the rest of the time. And while it's on, we can define it by some value. And so here, let's take this function. Here's an example impulse function. Here we have the Greek letter, the lowercase delta. So that's delta. So let's define delta sub a of t minus t naught. So this is a function of t. And we define it as 0. It's off. All right, the function is off as long as your time is between 0 and some number t naught minus a, where this a is the subscript on the delta function. Then we define it as 1 over 2a as long as our time is between t naught minus a and t naught plus a. And then it's defined as 0 the rest of the time. Now let's see, what does this mean? What does this graph look like? So let's build some axes here. And let's put, here's some t naught, here's some value t naught, and let's say here's t naught minus a, and here's t naught plus a. Now let's assume for a moment, and let's put a little bit of scale here. So let's suppose that there's 1 and there's 2 on the y-axis. Let's take a equal to 1. So if a equals 1, then the function is off, right, it's 0, and then between t naught minus a and t naught plus a, the function would be 1/2, right, if a is equal to 1, and then it's off again. Now what if, let's let a become small. So what if a is 1/2? If a is 1/2, then again it's 0 to begin with, but now when the function is on, we would have 1 divided by 2 times 1/2. 2 divided by 1 is, now it's 1. And then it turns off again. And what if, let's say a was equal to 1/4 now. Again, it would be off to begin with, and then when it's on, we would have 1 divided by 2 times 1/4, 2 divided by 1/2, and that would become 2. And so then it's on. And then if a becomes very small, so what happens if a becomes small? You know, how small? Well, you know, that's the tough part. How small do we want it? It's going to start by being off again. It's going to end by being off. But then while it's on, we get a very large output. So our function might jump way up here somewhere, right? Our function may jump way up here. And of course that interval, it becomes very small. So right, if a is a very small number, then t naught minus a to t naught plus a is going to become a very small interval and a very large value. And this is the concept of an impulse function. Now, to get to this thing called the Dirac delta function, we have to add in a couple of little pieces. Now that we know what an impulse function is, if we add another stipulation and say, well, if we have this thing that's called a unit impulse function. A unit impulse function has the added property that if we integrate over time, 0 to infinity, that impulse function, we get exactly 1. And that's how we define it. That's a unit impulse function. Now, the Dirac delta function is a unit impulse function, and it approximates that delta sub a that we talked about earlier, and it's defined by a special limit. If we take that delta sub a that we were talking about in the previous slide, and we take the limit as a approaches 0, we get this Dirac delta function. And so we define the Dirac delta function. Delta of t minus t naught is the limit as a approaches 0 of that delta function we discussed earlier. And this function, notice I'm putting function in quotation marks. It's not really a function as we've defined them in, through algebra. It's this thing called a generalized function that if you take some higher level classes, you'll learn more about. This function has the properties that Dirac delta of t minus t naught will define it as being an infinite value at that specific t naught, and otherwise it's 0. And if we integrate over time this delta function, we get exactly 1. And an idea behind the Dirac delta function might be if we hit something, really, right, at that moment, if you hit an object, a large amount of force is being directed into the object. But otherwise, there's no force being directed into the object. But over that short amount of time, there's an infinite amount of force. That's the concept behind the Dirac delta function. Now, we won't prove this. We will accept without proof that the transform of the Dirac delta function, so the Laplace transform of the Dirac delta function of t minus t naught is e to the negative s t naught. And we've got that listed on our transform sheet. There's our transform of the Dirac delta function, and there it is listed the same. So for example, if I wanted to find the Laplace transform of delta of t minus 7, all right, so I'm hitting an object really hard at 7 seconds after time begins. The Dirac delta, the transform of this delta function would be e to the negative s times 7, and we would normally write this as e to the negative 7s. All right, let's consider a spring mass problem again. We have an object weighing 16 pounds, stretches a spring 2 feet. The object is allowed to rest at equilibrium. Okay, so the object is stopped. Then 3 seconds later, the object is given a sharp blow. Right, it's hit. What happens? What's the position of the object at any time t? All right, so now if we think about it reasonably, right, you've got your object, and it's sitting there. And then 3 seconds later, something comes by and hits it. Well, what's going to happen? The position should be 0 for a while, and then it'll start moving after 3 seconds. Seems reasonable, right? Now let's model it with a differential equation, find the solution, and show that we get the same result. All right, so what do we need here? We have this weight, we need mass. All right, so we know that 16 is equal to mass times 32, all right, since we're using pounds, and so the mass is 1/2. We need the spring constant, so 16 is equal to k times 2, and so k is equal to 8. There's no damping in this problem that we're aware of. All right, so that tells me then I can model this with the differential equation 1/2 x double prime plus 8x. Now, what's my forcing function? 3 seconds later, the object is given a sharp blow. Delta t minus 3. There's the differential equation. All right, we need initial conditions. The object is allowed to rest at equilibrium. The initial position is 0. The initial velocity is 0. See, now we couldn't have solved this back in when we were talking about these types of problems originally, because we can't use undetermined coefficients. We can't use variation of parameters with this type of forcing function. But we can use the Laplace transform because we've learned this now. So we find the Laplace transform of both sides. Alright, so the Laplace transform of 1/2 x double prime. Well, let's see, that would be 1/2. And then the Laplace transform of x double prime. That's s squared capital X minus s y of 0 minus y prime of 0. And this shouldn't have x's, sorry. These should be x's, lowercase x's. So minus s x of 0 minus x prime of 0 plus 8 capital X. The Laplace transform of x of t is capital X. And on the right-hand side, the Laplace transform of the delta function is e to the negative s times 3, e to the negative 3s. Alright, now x of 0 is 0, x prime of 0 is 0, so this term, those both go to zeros. So I now have 1/2 s squared times x plus 8x is equal to e to the negative 3s. Let's get rid of the fraction. I'll multiply through by 2. S squared x plus 16x is equal to 2e to the negative 3s. Factoring x by s squared plus 16 is equal to 2e to the negative 3s. So then x is equal to 2e to the negative 3s times 1 over s squared plus 16. Then to find x of t would be the Laplace inverse of that whole thing. Alright, so now to find the Laplace inverse of this, well, let's think about this a little bit. If we want to find the Laplace the inverse, this 1 over s squared plus 16 should have you thinking about a sine function, right? This should have you thinking about sine of 4t. Okay, but I would need a 4 in here, which means I'd need to divide by a 4. But now that e to the negative 3s, what does that tell us? Alright, so if we go back and let's look at our possibilities here. Alright, remember that e to the negative, if we see that e to the negative as times f of s, that's telling us to use the second translation theorem. We're going to need a unit step function here. And since a is, what was a in this case? It was 3, right? A was 3. Yeah, a is 3. So then I'm going to need f of t minus a, u of t minus a. Alright, so bringing that back up, now I know it's going to be a sine of 4t, but it's not t, it's t minus 3. And so then x of t will be 2 over 4, 1/2. And then I'll have sine, not of 4t, but of 4 times t minus 3. And I need to multiply this by the unit step function of t minus 3. And so there's our position function. And if we think about this, right, that u of t minus 3, remember what that means is the function is 0 up until 3 seconds. And at 3 seconds, something happens, right? We get some sort of motion. So now let's actually look at a graph of this function. I'm going to use the program called Desmos to do this. So Desmos is an online application. And it doesn't have the built-in unit step function. You have to define it first. So let me define u of t as being a piecewise function. Here's how we do this on Desmos. If t is less than 0, we'll define the function we'll define it at 0, and if t is greater than or equal to 0, we'll define it as 1. And we see here the unit step function. Notice with less than 0, function is 0, and then it jumps to 1 the rest of the time. So there's our unit step function. Now I'm going to turn that off, and now let's define our position function. I'm not going to use x, I'm going to use f. So I'm just going to use f of t now, is then equal to 1/2, and then we had sine of, not sing, sine of 4 by t minus 3, but that was being multiplied by the unit step of t minus 3. And there's the graph of the function. And we can see, as expected, the position was 0 until it was hit, right? Something came along and hit the object, starting the motion, and at 3 seconds, right, at 3 seconds, then the motion starts and has whatever amplitude. All right, so there's how we can model that graphically, and so if we see a problem like this, where we see the phrase "a sharp blow" or "hit" after however many seconds, let's go ahead and just assume that we're using the Dirac delta function to as our forcing function and build that in. All right, so here's another example. Here's another problem, and that would be a good time to pause. Try this one out on your own. All right, we have an object weighing 32 pounds, stretching a spring 2 feet. The object is released from a point 1 foot below the equilibrium. 2 seconds later, the object is given a sharp blow. All right, so it's allowed to start motion, and then it's hit. All right, so then what happens? All right, so let's see what we have here. Let's build our problem. We have 32 pounds again, and so that would be m times 32, so m equals 1. All right, the mass is 1, and we have 32 pounds is equal to k times 2, so k is 16. Right, and so then we would have x double prime plus 16x is equal to delta of t minus 2. 2 seconds later, the object is given a sharp blow. Let's see, what's my initial conditions? The object is released from a point 1 foot below the equilibrium position. So its initial position is 1. Remember our convention. Below equilibrium is positive position. And it's released, so its initial velocity is 0. All right, we apply the Laplace transform. All right, so that would give us s squared capital X minus s times x of 0 minus x prime of 0 plus 16 capital X is equal to e to the negative 2s. All right, now let's see. X of 0 is 1. All right, so this becomes a 1. And x prime of 0 is 0. Let's do a little factoring here. So I have x, capital X, times s squared minus 16 is equal to, let's bring that term over, s plus e to the negative 2s. So then x, capital X, is equal to s over s squared minus 16 plus e to the negative 2s times 1 over s squared minus 16. And that should be, those should all be plus 16. Sorry about that. Plus 16s, not minus. All right, and so then x of t would be the Laplace inverse of that right-hand side. All right, now s over s squared plus 16, that's fairly easy, right? That you should immediately be thinking of a cosine there, cosine of 4t. Now here we have a 1 over s squared plus 16, so let's multiply by 4 and a 1/4, and that e to the negative 2s tells me we have to translate 2 units and use the unit step function. So then x of t is going to be cosine 4t plus 1/4 sine 4, but not t, t minus 2, and then unit step of t minus 2. All right, and so we see we had some motion to begin with, the cosine 4t motion, and then after 2 seconds, the motion changes. Let's see what the graph looks like. I've already got Desmos up, so let's go ahead and take a look at this function. All right, so cosine of 4t, and then plus 1/4 sine of 4 by t minus 2, and then times the unit step function of t minus 2. And so let me just try and zoom in a little bit. We have the normal motion, and then things change at 2 seconds. And one thing to notice right away, look at the amplitude of the curve, right? Look at the amplitude before 2 seconds and then after 2 seconds, right? Notice the amplitude changes. At 2 seconds when the object was hit, it changed the motion of the object. And we can see that as a result, particularly with the change in the amplitude of the curve. All right, so that concludes what we need from dealing with the Dirac delta function.